Okay, so in lesson number 3, we're going to start looking at a new type of function called a logarithmic function. So we're going to start off with a review of what an inverse is. So in lesson number 1, we learned that there's a couple of ways of defining or determining the inverse of a function. If the function is defined by a set of ordered pairs, the inverse is defined by interchanging the x and the y coordinate. So if I had an x-coordinate that was 3 and 7, the inverse would become 7 and 3. If I have an equation, the inverse could be determined by interchanging x and y and solving for y. So if I had y equals 3x minus 2, I would interchange it and get 3y minus 2, and then I would solve for y. So I would add 2 to each side and then divide by 3. This I could rewrite as 1/3 x plus 2/3 equals y. And then graphically, I can take my graph. So if this was my graph, let's say my graph went like this. What I could do is I could reflect it in the line y equals x. So that was that mirrored line. In which case my reflection would become this. So that's what I could do graphically. Another point to recall, the domain of the inverse was the range of the original function. The range of the inverse was the domain of the original function. So if I have this equation right here, or this graph I mean, it says draw the graph of the inverse of the function whose partial graph is shown on the grid. So I can draw my mirrored line. I'm going to use a ruler, so to speak, to draw that. So here's my mirrored line. So points on my line are things like 5 and 5, 4 and 4, 3 and 3, 2 and 2, etc. So if I was to reflect about this line, what I would choose to do is I would still pick coordinates on the line, such as this coordinate being 2 and 0. I would interchange that to get 0 and 2. This one that is 0 and 4, I would interchange that to get 4 and 0. Now that I have 2 points, join those 2 points with a straight line, and there becomes my new line. So this becomes my inverse. And if you notice, this is a reflection of the line in black. Okay? If the function passed through the points 10 and negative 16 and negative 10 and 24, what would be the points that would lie on the inverse function? Well, again, the inverse is interchanging this. So if I interchange these, I would get negative 16 and 10, and then 24 and negative 10. Those would be the points on the inverse graph. And then finally, if I have the equation, y equals 4 minus 2x, the inverse equation, I interchange the x and the y. And what I get is x equals 4 minus 2y. What I would probably do at this point, just to avoid the negative use, bring the 2y over, and then move the x over. And then my last step would be to divide everything by 2. So I get 4 divided by 2, which is 2. And x divided by 2. And the last thing is, instead of putting it as an x divided by 2, I'd probably pull and separate that and have a 1/2 times x. It's just because then that becomes a y equals mx plus b. Now I can see what my slope is, I can see what my y-intercept is. Okay? So in this next part, we're going to be doing several investigations. So what the prompt is going to be is I'm going to get you guys started, and then what I'm going to do is tell you guys to actually go through and start doing some of this on your own and then check back. So in this example, we're going to consider the exponential function y equals 2 to the power of x. And we're going to look at this algebraically. So if we were to algebraically look at the inverse, just like we were doing with the other page, the instructions are to interchange the x and the y. So what I would get is x equals 2 to the power of y. Then I encounter a problem. The problem comes in, how do I get y equals? How do I bring the y forward? So what strategies do you have for when y is in the exponent? Well, at this point, the only strategy that I have is to y root it. So I could try something where I take the y root of x and the y root of 2 to the power of y, because these are going to cancel out. But now I have y as the index of a radical. That didn't get me anywhere closer to what I need to do. So the problem is I can't isolate y. So does that mean that we can't find the inverse of this equation? Well, let's look at the graph. So if you look at part 2, it says to determine the inverse graphically, we can switch x and y coordinates. So what we're going to do is we're going to start off with graphing y equals 2 to the power of x. This was the graph that we did in lesson number 2. So if you want, you can go through and you can pause it and go back to lesson number 2 and see what that chart looked like. Or we can keep going and, oops. And solve the components of this graph. So 2 to the power of negative 3 gives me 1 over 8. 2 to the negative 2 gives me 1 quarter. 2 to the negative 1 gives me 1/2. Then I get 1, 2, not 3, 4, 8, and 16. Erase those and take them in better. 4, 8, and 16. So if I was to graph these these points, negative 3 and 1/8, negative 1 and 1 quarter, negative 1 and 1/2. Notice my scale is going up by 0.5s. 0 and 1, 1 and 2, 2 and 4, 3 and 8. And then I don't have the ability to graph 4 and 16 because it goes off my page. So if I was to join these points with a smooth curve, this becomes my curve. This is y equals 2 to the power of x. So if I was to look at the inverse, interchange x and y, that's how I do the equation. A set of ordered pairs, I interchange the x and the y coordinates. So what that would mean is negative 3 would become y, x would become 1/8. Negative 2 becomes y, x is 1 quarter. So this becomes my new x row. So now, if we looked at graphing these, what I would get, when the value of x is 1/8, which is going to be very small, I get negative 3. When it's 1 quarter, I get negative 2. When it's 1/2, I get negative 1. When x is 1, y is 0. And then I get 2 and 1. 2 and 1, 4 and 2, 8 and 3. And I can't go to the 16 and 4 because I can't reach it on my graph. So if I joined these points with a smooth curve, this is the graph that I would get. So this would be the graph of x equals 2 to the power of y. So if you look at these two graphs, there is a mirrored line of symmetry. And that was the line that we identified in lesson number 1 and earlier in this lesson. And that was my line of my y equals x. So that becomes this line. And I'm just going to make it a different color. So if you look, now that I have this mirrored line in there, you can definitely see that this is a reflection. So the equation of that line is that y equals x. So we've shown that, yes, we can find the inverse of this exponential function. So if we can find the inverse of this function, there has to exist a way to be able to write this as a y equals. Because generally, x's are our input values, and y is what we're solving for. Which means I should be able to solve this for when x equals 512. I should be able to find a y value. This becomes our new function. This is called a logarithmic function. So really, in essence, what a logarithmic function is it's the inverse of an exponential function. So the inverse of an exponential function with a base of 2, example, y equals 2 to the power of x. When I inverse it, I get x equals 2 to the power of y. To pull that y out front, I take the log. So what I get is I get log base 2 of x. That becomes my new equation. So instead of writing the equation as x equals 2 to the power of y, it becomes written as y equals log base 2 of x. And this is the equation we generally write, rather than this equation, because then we have the y out in front. So if you look at parts of this logarithmic base, the value of x for our studies is always going to be greater than 0. It could be any real number, but it has to be greater than 0. The bases that we look at are going to be greater than 0, and b is never going to be equal to 1. And that's for the same reason why in this equation here, the base was never equal to 1, because I don't actually have an exponential function when the base is 1. So there's parts on here that you should know the terminology. The value of the logarithm is what y equals. The base of the logarithm is that little, almost like a little index or a little subscript. And then the argument is my x values. So if these were our two graphs that we drew from the previous page, and we complete parts of this graph, this was my y equals 2 to the power of x. This was my inverse graph, which I was writing as x equals 2 to the power of y. I now know that I can write this as y equals log base 2 of x. So if we examine each of these two functions, we'll start off with this graph. So I'll put that one in blue. The domain of that graph, the possible x values, well, this line is going to keep continuing, and it's going to keep continuing along the x values, positively and negatively. So the domain of this is that x could be any real number. There's no restriction on what x could be. My range, however, this line will get closer and closer to the x-axis, but it'll never actually go over the x-axis. So to write my range in set builder notation, the set of y values such that y is bigger than 0, and y could be any real number bigger than 0. Where does this graph cross the x-axis? It doesn't. So there is no x-intercept. Where does it cross the y-axis? Right here. It crosses the y-axis at 1. And then I have this horizontal asymptote, this x-axis, where it comes close to but never comes over. As an equation, that x-axis has the equation of y equals 0. So now, if we look at our log graph, this one, the inverse graph, what's the domain of that graph? Well, this graph, again, is getting closer and closer now to the y-axis, but it's never going over. So in this case here, I'm not getting negative x values, and up here, we were told that the base is always going to be, the value of x is always going to be greater than 0. That's part of my restriction. So my domain this time is that x has to be greater than 0, but x could be any real number as long as it was greater than 0. My range this time, I can have negative y values. They're just going to keep getting smaller and smaller. And my y values on the other end are going to keep getting bigger and bigger. So I have no restriction. Y could be anything. The x-intercept this time, does this graph cross the x-axis? Yeah, right there, at 1 and 0. So this has an x-intercept. Does it cross the y-axis? No. It never crosses the y-axis, so I don't have a y-intercept. And then the asymptote, that imaginary line that it never crosses, well, this graph is getting closer and closer to the y-axis without going over it. The equation of the y-axis is that x equals 0. So something to notice, the range of the inverse was the domain of the original. The domain of the inverse was the range of the original. Everything is being interchanged. The point 8 and 3 on the log graph corresponds to the point 3 and 8. So let me just show you where those 2 points are. So the point 8 and 3, which you can't even see on your graph, which would be right here, this point here corresponds to 3 and 8. Better to look at it, the point 4 and 2 corresponds to the point 2 and 4 because they're inverses of each other. The point 3 and 8 on the graph of y equals 2 to the power of x means that 8 equals 2 to the power of 3. The point 8 and 3 on the log graph means that 3 equals log base 2 of 8. We can use our graphing calculator to sketch logarithmic functions. The way that we do this, if I'm doing my exponential function, that's not going to be the problem. 2 to the power of x, we're done. To do the other function, to do the logarithmic function, what we have to do is we have to write this log base 2 of x as log x divided by log 2. And we're going to investigate why we put it in that way in the next couple of lessons. What it comes down to is my calculator doesn't have a way, or the majority of the calculators we're using does not have a way to change the base of the calculator. So we have to put the base in as a division. So what we're going to do now is we're going to look at what the value of b, what that base does in my logarithmic functions. So it says the graph of log base 3 of x is shown. So to graph log base 3 of x in my calculator, I would have gone log x divided by log 3. Okay? In each of the following, you're going to sketch the graph on a graphing calculator, and you're going to determine the missing coordinates in the statements, and then sketch the graph on the grid. So if I look at the first one, log base 5 of x, and to put that into my graphing calculator, it will become log x divided by log 5. So if I grab my calculator, y equals, I clear this off, and if I type in log 5, so here's my log button, so this becomes log x, sorry, not log 5, log x divided by log 5. And it changed my window settings to be what I see here. So I go to my window button. My window x min is -1. Max is 11. Going up by ones. My y goes from -4 to +4, going up by ones. So now if I graph this, this is the graph that I get. And the question that is asked is, what is the equation, or what is the points? So on my calculator, if I press the trace button and then I go 1, on my calculator x equals 1 comes up, press enter, and I get 0. If I go 5 and press enter, I get 1. So my 2 points are 0 and 1. I'm going to use those 2 points to kind of help me sketch the graph. So I have this 1 and 0. That's the same point as the last graph. And then I have this 5 and 1. So then this graph comes up like this. And this is my y equals log base 5 of x. So now if I look at log base 1/3 of x, I'll use a different color, one. So this one I get log base or log x divided by log 1/3. That would be this equation. So if we go back to our calculator, y equals, clear that out, log x divided by log 1/3. So there's my log x divided by log 1/3. Press graph. My graph goes in the other direction. Instead of starting small and getting big, it starts big and gets small. So if I was to type in my 2 x values, trace, when x equals 1, I get 0. And when x equals 1/3, which I can type in as 1 divided by 3, and press enter, I get that y equals 1. So I get 1 and 0, and 1/3 and 1. So if I was to graph these 2 points, here's my 1 and 0, and then my 1/3, so when x equals 1/3, y equals 1. So this graph looks like this. So this is my y equals log base 1/3 of x. Now I want to quickly show you something. If I was to do a second graph, and I went log x divided by log 3, and graphed that, that's the graph that's in black. Notice these 2 graphs are a reflection of each other. So if I look at the last one, log base 1/5 of x, if these 2 are reflections of each other, the black and the blue, what do you think the 1/5 x should be? Should probably be a reflection of my 5. I'm just going to change the color. So if I graph this, okay, I'm a little bit lazy. Instead of rewriting the whole thing, I'm going to change the 1/3 to a 1/5. And since I have the equation here, I'm going to change this 3 to a 5. So I press the graph button. There is my log base 1/5 of x. And then the second graph, this right here, this was my log base 5 of x. So again, you can see that they're reflections. If I wanted to find these values out, when x equals 1, I get that y equals 0. And then if I go x equals 1 divided by 5, I get that y equals 1. Okay? So I get 0 and 1. Okay, I think I missed part of this last part. So again, if we start looking at our last equation, log base 1/5 of x, to put that on my graphing calculator would become log x divided by log 1/5. If I put that into my graphing calculator, what I can do is I can scroll over to where I have my log x divided by log 1/3, change the 3 to a 5. And if I had graphed that log base x divided by log 3, so that was this graph here because I was showing you the reflection, it would become log x divided by log 5, which I already have changed. If I graph my two graphs, there's my log base 1/5 of x, and there's my log base 5 of x. So this becomes my graph that I have in red. And what we can see is that they are reflections of each other. My graph is a little bit off, but they should be drawn as reflections of each other. And then we have those two values. The value of y when x equals 1 is 0. And when x equals 1/5, I get the value of 1. I just changed the 1/5 to a decimal. So I get 0 and 1. So we notice that all of my graphs seem to be going through this point. Now, the chart on the next page asks us to fill in for the domain, the range, the x-intercepts, and the y-intercepts. So if I look at the domain, my possible x values, if I look at this graph, what do I notice about my x's? Well, they never go into the negatives. X has to be greater than 0. So there's two ways that we can write that. We can write x has to be greater than 0, but x is a real number. That's my set builder. Or I can write it that x has to go from 0 to infinity. Putting curved brackets because it doesn't actually equal 0. And infinity it can't equal because infinity is like just, it's a concept, it's not a number. And my graphs are the same for all, or my domains are the same for all 4 graphs. Then when I look at my ranges, which I already have written up, my ranges show that it could be anything. Because if I look at this graph, my graph in black and green, as the value of x gets larger, these values of y are also going to start to increase. And then if I look at these two graphs, the same thing's going to happen. The value of y is going to decrease. So my range for all of these becomes y is a real number. Or in set builder from negative infinity to positive infinity. Now my x-intercepts can be the same for all of these. It goes through 1. The y-intercept, there is no y-intercept. This never crosses the y-axis. And then we have the asymptote. That was that imaginary line, which in our case is the y-axis. As an equation, the y-axis is x equals 0. And then finally, the value of x when y equals 1. So if I go back to these graphs, it's the value of x when y equals 1. That's 5 and 1. 1/3 and 1, 1/5 and 1, and 3 and 1. So if we write those into our chart, I have 3, 5, 1/3, and 1/5. So that brings us to the last line, which is the general line. Y equals log base b of x, where I don't know what the base is. What would the domain of this function be? Well, given the pattern that we've discovered, the domain is going to be the same. X has to be greater than 0. The range is going to be the same thing. Y is a real number. The graph is always going to cross through 1 on the x-axis. And it's never going to cross the y-axis. The asymptote is always going to be that y-axis line, which is x equals 0. And when y equals 1, x is going to be the base. Okay? If I look at the next question, it says state the bases of the functions whose graph are increasing from quadrant 1 to quadrant 5. If I look at my quadrants, this is quadrant 1, 2, 3, 4. So if the graph is increasing from quadrant 1 to quadrant, quadrant 4 to quadrant 1, that's this type of a graph, and increasing. The two graphs that showed that pattern were these two. So a base of 3 and 5. And then the graphs that are decreasing from quadrant 1 to 2, or 1 to 4, sorry, looked like this. Those were these two, the fractions. So 1/3 and 1/5. Just a realization that if the base is a number greater than 1, I'm going to have an increasing graph. And if the base is between 0 and 1, my graph is going to decrease. Okay? So now we're going to take a look at two special log functions. Common logs and natural logs. So common logs are a log with a base of 10. So it's kind of like when we do square roots. If I go square root of 4, we know that the index is supposed to be a 2. I don't have to write it in. Well, with logs, if I write log base x, it means log base 10. So instead of, if I had log base 10 of x, instead of having on my calculator to go log x divided by log 10, I can simply type log x. So let me show you this on the calculator. So if I go y equals, I'm going to clear both of my graphs. I'm going to start off with typing in log x divided by log 10. That's the way that we were doing all the rest of our logs. Graph this, and there's my graph. But what I'm saying is I don't have to write all of this because I've got this common log. If I simply type in log x, I'm going to get the same graph. And I'll show you by changing the thickness of the line. So if I scroll over and press enter, that line is going to get thicker. I press graph, and notice it's drawing it over top. I can further prove it by looking at my table and noticing that the values are the same for my x inputs. The other type of log that we have is a natural log. So a natural log has a base of e, which we looked at in the last lesson. It's that irrational number has an approximate value of 2.718. So again, I can verify this on my calculator. And I can type in, so I can go log x divided by log e, and to get e, it's the second function of this ln. Exponent would be 1. If I graph this, this is the graph that I get. But what I'm telling you is if you have a base of e, I don't need to do that whole log x divided by log e. I can simply put in natural log of x. And if I graph this, I get the same graph. Okay? So what that means is the natural log of x and y equals e to the power of x are inverses of each other. Just like y equals 10 to the power of x would be the inverse of y equals log x, because this 10, I don't need to write in. If I don't have it written there, I understand the base to be 10. So now we're going to look at what the value of a does to this function. So in this case here, what I'd like you to do is pause for a moment and actually graph these 4 equations for yourself on the grid, and then you can turn this back on and then check to see if your graphs match mine, and then see if you can answer these questions. So here are my 4 graphs, the 3 that I've drawn in. So I've got the green, the orange, or red, and blue. Did any of these change with this? Did the domain change? No. The range? No. The x-intercept? Still going through the same point on the x-axis. The y-intercept, this didn't cross the y-axis at all. And the asymptote still remained my y-axis. So there were no changes for any of these. Okay. Well, what happened if I changed the base? If instead of using 0 and 1, or sorry, instead of using 3, what if these were all 1/3? Would there be any change? So take a moment and put this into your calculator and see what happens. So if I graphed y equals log base 1/3 of x, and y equals 2 times log 1/3 of x, y equals negative 0.5 log base 1/3 of x, or y equals negative 2 log base 1/3 of x. Would I change the domain, the range, the x-intercepts, the y-intercepts, and the asymptotes? No, I wouldn't. There would be no change. So there's no difference if the base was between 0 and 1/3. So we have the shapes of logarithmic functions with the equation y equals a times log base b of x depends on both the value of a and b. So if we were to look at the graphs that we were doing and put together some patterns, when the value of a is greater than 0, so when the value of a is greater than 0, such as here, the value of a would be 1, or the value of a would be 2, my graph rises from quadrant 4 to quadrant 1. When the value of a is less than 0, it drops. So instead of rises, it falls. So the graph falls, or I could say decreases from quadrant 1 to quadrant 4. If I look at when my base is a fraction, something like 1/3, 1/5, between 0 and 1. I shouldn't say fraction because I could have a fraction bigger than 1. But if my fraction was between 0 and 1, such as what we did here, and my value of a was greater than 1, so if I looked at these 2 equations here, which just to show you on the previous page, 2 pages back, were these graphs right here. In the case here, when the value of a was greater than 1 or greater, my graph fell from quadrant 1 to quadrant 4. The same thing happens when I have a value greater than 0, such as 1, such as 2. So in this case here, the graph decreases from quadrant 1 to quadrant 4. And then finally, in this last one, if the value of a is less than 0 and the base is between 0 and 1. So that's looking at these 2 equations from before. And what you'll notice is in those 2 equations, the graph actually rose. So it would be the same as what I have here. The graph increases from quadrant 4 to quadrant 1. So now we're going to put all of this together and do a couple of examples, and then you'll have your practice questions. So we're going to start off with summarizing the characteristics of a logarithmic function. So this is taking all of the stuff that we've done in the previous 6 pages and putting it all together. So on all of these graphs, the x-intercept stayed at 1, always at 1. And there was never a y-intercept. The domain stayed the same every single time. The set of x values such that x was greater than 0 and x was a real number. Every time. The range stayed the same each time. It was a real number. Okay? The y-axis became a vertical asymptote, and the equation of that vertical asymptote was that x equals 0. And then what we have here is the summary of the chart just from the previous page. When the value of a and b, so in my equation y equals a times log base b of x, when these two values were both greater than 0 and greater than 1 respectively, the graph increased. So increases from quadrant 4 to quadrant 1. If I change my b value to be between 0 and 1, the graph would then decrease. If I change my a value to be less than 0, so I make a negative, but my base is still greater than 1, the graph would increase from quadrant, or sorry, not increase, that should be decreases. That's my bad. And then finally, if the value of a was negative and my base was between 0 and 1, the graph increases. Okay. Log base b of x is equivalent to x equals b to the power of y, and it's the inverse of b to the power of x. B becomes the base of both the logarithmic function and the exponential function. So if we look at class example number 2, it says state the inverse of the following functions. Answer in the form of y equals. So if I was to look at this, what I have to remember is this right here. Y equals log base b of x is equivalent to this. So if I took this equation and I rewrote it, that means it should be 3 to the power of y equals x. The inverse of that, interchange these two, I get 3 to the power of x equals y. If I look at the other one, I've got y equals 8 to the power of x. The inverse of that would be x equals 8 to the power of y. And to pull that y down in front, I have y equals log base 8 of x. Okay. Class example number 3 says, which of the following could not represent a function with the equation y equals a times log base b of x? Okay. So if I look at these 3 equations, and I remember the things that I was told. Y can be any real number, meaning it has to go above and below the x-axis. So could this be a graph of the function? Yeah? I'm not even looking at what this is, whether or not this is 1 or 0. It could have this shape. It's not crossing the y-axis, and it is crossing the x-axis. This shape could also happen for the same reason. The one that can't happen is 3. because it's not showing that it crosses the x-axis. So this one is not showing, so the range should be any real number, meaning this should cross the x-axis. Here are the questions that I would like you to do. Questions number 1, 6, 8, and 9.